Alright, so in today's lesson we're going to study something known as the electromagnetic induction. Okay? So it's part of electromagnetism and we're going to induce electromagnetism in the reverse direction. Um, I'm going to demonstrate how that works, what that looks like, and then we're going to define some key terms and some basic rules that govern how electromagnetism works. Okay? How electromagnetic induction works. Sorry. So first of all, I'm going to just repeat what we did just a moment ago. So we've got a DC motor that's connected here. When the power supply is turned on, well, the greater the current flowing through, the greater the speed, right? So we've already discussed just moments ago, okay, how the speed would be affected by the amount of current that's flowing through it. If I ask you to describe the energy changes associated with the DC motor, could you tell me what energy changes are taking place in this case? Side पे इधर लिख देता हूँ जी
Potential energy.
No, it's not potential energy.
There's going to be kinetic energy.
You started off with
Electrical energy.
electrical energy. Okay. इसको मैं भी erase कर दूँगा थोड़ी देर में. So you started off with electrical energy and
Movement of particles and kinetic.
you went to kinetic energy, right? So you're converting electrical energy into kinetic energy, and of course there's going to be some sort of motion. It's going to heat up, so some thermal or heat energy would also be produced in the process. Okay? So this is the forward direction that you've just seen with the DC motor. Would you agree that a DC motor doesn't store energy? It's not a reserve, a source of energy as such. It's not a source of potential energy as such.
I think yes, because till
It's just a transducer. It's just converting energy from one form to another. Okay, fine. So I'm going to do something fishy now. I'm going to connect the DC motor in much the same way as before. Okay, so I've got the two terminals of my DC motor connected to my two wires, and those wires will then be connected to a device known as a galvanometer. Okay? A galvanometer is simply an instrument, a device that tells you the direction of the flow of current. So simply you could say, अगर इसको हम circuit diagram इसका एक बनाते हैं अच्छा सा. So you've got the left hand side, which is the red wire. You've got the right hand side, this is the black wire. You've got the two sides connected as follows. And on a circuit diagram, this might look like a motor connected to a galvanometer. Remember, the galvanometer just tells you the direction of flow of current. Okay? So it deflects in one direction when current flows in one direction, and it deflects in the opposite direction when the current flows in the opposite direction. Chalo. So would you agree that this is basically what we've just set up?
yes.
Yes? Alright. Do you see a power supply or a store of energy, perhaps a battery, a cell, a mains supply, any sort of source of energy जिसको आप कहेंगे कि okay, this is where the energy is coming from.
No.
This is where current will come from.
No.
So you don't see anything like that.
Is that the galvanometer?
Sorry?
Is that the device?
Galvanometer is just an instrument. It's like an ammeter. It's just like a voltmeter. It only reacts to a flow of current because it's supposed to show the deflection. It deflects on the basis of the direction of the flow of current. Okay? So it will deflect in one direction when current flows in one direction, and then it will deflect in the opposite direction when current flows in the opposite direction. That's all it does.
No, I don't
So you don't see an electric current supply. You don't see anything like that. But so it's not deflecting in any direction either. But something fishy happens if I take this motor and simply give it a whirl. तो मैं इधर से पकड़ता हूँ and I rotated the rotating part of the motor, and did you see that the needle deflected a bit? Let's try that again. So what's going on? So this instrument is basically showing us that there was some flow of electric current in some direction. That's what caused it to deflect. And I took a motor that essentially is supposed to take electrical energy and convert it into kinetic energy, and I've gone in the reverse direction. So this time I started with kinetic energy and went to electrical energy, and of course heat, because there's motion, there's going to be rubbing of
Friction.
different components, so there's going to be friction, right? So this is what I've done using the same transducer. Well, this effect, where you start with some kinetic energy and you cut some magnetic lines of flux. Now this is an introduction to electromagnetic induction, and that resulting in some electrical energy, this is known as electromagnetic induction. Okay? So this is how it works. Let's erase that. Let's start writing some of the key points, right? So what I've just done is demonstrated electromagnetic induction at work, and now I am going to define electromagnetic induction, right? So I'm going to define electromagnetic induction. So electromagnetic induction is a process through which an electromotive force is induced due to a changing magnetic field across a conductor. Okay? I hope कि आप भी इस चीज को लिख रहे हो. So in essence what's going on is this now. So electromagnetic induction को थोड़ा सा अच्छे तरीके से describe करना शुरू करते हैं. I've got a DC motor. We've already seen that the DC motor has an external pair of magnets. There's an external magnet set, and there's a coil of wire that's rotating inside, right? So there's an external magnetic field and there's a coil of wire inside. And when you pass current inside that coil of wire, the motor effect takes place, and so the coil of wire rotates. That's what happens, right? So this time what's happening is you have the same external magnetic field. You can see it with the compass. So the compass is attracted at one end. When you rotate the motor, the other pole is being attracted now. Okay? You can see that at work. So you can see there is an external magnetic field, and there is a changing magnetic field across the conductor. In other words, when you're moving the conductor with your hand, when I give the turning spindle a flick, basically what did I do? I was rotating the coil of wire across those field lines. So what happened was those magnetic field lines were being cut by that conductor. So whenever that happens, whenever you cut some magnetic field lines with a conductor and you complete the circuit, some electric current will flow. Okay? This is basically what Faraday's law tells us as well. So Faraday's law में Faraday's law, scientist Michael Faraday, he discovered this law. He discovered a relationship that governs electromagnetic induction, and he found out that the magnitude, meaning the size of the electromagnetic force, remember, is a type of voltage. So the magnitude of the electromagnetic force is directly proportional to the cutting, the rate of cutting of magnetic lines of flux, magnetic field lines of flux, ताकि आप लोगों को समझ में आसानी रहे, lines of flux. ठीक है? So in simple terms, what that means is, the greater the number of magnetic field lines that are being cut by that conductor per unit time, the greater the EMF will be produced. जिसको अगर आप mathematically अगर देखना चाहें तो you could just say, this is not part of your main link, लेकिन just for the sake of your understanding, so electromotive force or voltage would be equal to the change in magnetic field lines of flux divided by time taken. So it's the rate at which that's happening. So the greater the number of lines of flux that are being cut per unit time, the greater the electromotive force will be. And this is achieved by two ways. Can you think of a few ways? Can you think of a few ways by which we could increase the number of field lines being cut per unit time?
By increasing the speed of the conductor.
So by increasing the speed at which the conductor moves relative to the magnetic field line, okay, the speed of rotation, that's good. So इसको अगर चलो side पे लिख देता हूँ मैं. So the speed of rotation, so factors that affect the EMF produced. Number one, that's the speed of rotation. What else? How else can we increase the
Speed of rotation.
number of lines of flux being cut?
Not
So-
sure, I guess by inducing more current, giving more current.
No, you're not inducing current, you're not starting with current. You're starting with kinetic energy this time, right? So could you use stronger external magnets to increase the number of field lines in space, right? So use stronger external magnet that would increase the number of field lines, the concentration of those field lines. Okay, fine. What else could you do? Would it make a difference if I just have a single wire that I'm cutting those field lines with, as compared to maybe 100 wires cutting the field lines simultaneously, maybe in the shape of a coil?
Yes, but how is that possible?
So instead of having a single wire, let's increase the number of turns. The number of turns. So increase number of turns in the coil, and perhaps creating a stronger magnetic field as it's produced by simply introducing a soft iron core inside the solenoid. So use soft iron core. in solid light, right? So all of these basically affect the overall number of field lines that are being cut per unit time. Okay? So that was Faraday's law, and some factors that help us govern how much voltage will be produced. Okay? Now we are able to determine the magnitude of the voltage that's produced. Well, that's fine, everything is perfect. But how to determine in which direction will the current be flowing? So how do you know which one is positive, which one is negative without using eagle value meter? So we need some rules, right? तो मतलब आप हर जगह जाके वो machine खोल के let's just open it up, we'll splice it, we'll split it open and we'll make galvanometers of the use कर लो. ये काम करना तो थोड़ा मुश्किल हो गया है. So we need some other mechanisms. ठीक है? इससे तो हमें सिर्फ साइज का पता चला, साइज ऑफ वोल्टेज. हमें ये नहीं पता चला कि पॉजिटिव साइड किस तरफ है, नेगेटिव साइड किस तरफ है. ठीक है? तो उस चीज के लिए we use something known as Lenz law. ठीक है? So Lenz law basically governs, or doesn't govern, लेकिन helps us determine the direction in which that current will be flowing. Okay? So Lenz law just tells us that the direction of the induced current due to that induced EMF, the direction of induced current will always be in a direction such that it opposes the change causing it. Okay? So the direction of that current that's going to be induced, that conventional current, will always be in a way so that it would oppose that change that's causing it. What does it do? So, say for example, you've got a solenoid. Okay? And you're trying to introduce a magnet inside it. So, say for example, you've got the north pole towards the right and the south pole towards the left. And you're going to try and push the magnet into the solenoid. So what's going to happen is that magnet and its field lines going from north to south, of course, right? So all of these field lines originating in north, they're going to start getting cut by these wires, these turns, right? By this solenoid. आप ये चीज note करेंगे, okay? Which means that there should be an EMF induced according to Faraday's law. Yeah? And the more these lines of flux are being cut by this conductor, the more EMF should be produced per unit time. अगर per unit time हम सारी चीज consider करें. Fine. Now, according to Lenz law, the direction of the current would be in such a direction such that it opposes the changes causing it. So, for example, अगर इधर north है and you're moving the magnet into the coil, it will try to oppose that change by bringing another north at the left hand side to repel the north from coming in. It tries to oppose the change causing it. And if you know the direction of the magnetic field, well, you can use, what can you use?
The right hand.
You can use the right hand grip rule to determine the direction of current. So if you want your north to be towards the left, the curl of your fingers shows you that the direction of the current would be curling forwards into the page, right? So that would give you the direction of the current that is induced. समझ रहे इस चीज को? So with your right hand grip rule, you can see that the direction of the induced current would be towards the board or into the board. Okay? Now let's say the magnet is already inside. Are you going to try and pull it out? So this time it's going to try and resist that motion. So it's trying to resist you from pulling it out. So this time, in order to resist that, it's going to create an opposite pole at the left hand side, a south pole at the left hand side, to try and retract that magnet as you try to pull it out. So it's opposing your motion. Okay? And again, you can use your right hand grip rule to determine the direction in which current flows. So this time the direction is reversed, right? So this time current flows in the opposite direction, coming out of the board, right? Because north is found towards the right. So it's coming out of the board. So this time it's in the opposite direction. So these were the two rules we wanted to cover today. They're incredibly important rules because they help us understand how electromagnetic induction works. Okay? It helps us understand how kinetic energy can be converted into electrical energy and of course heat, which is not the useful form of energy. Okay? And this is basically the principle that is used in generators, when we use generators to produce electricity, in dynamos जो कि cars के अंदर लगे होते हैं to produce electricity, in nuclear reactors जिसके अंदर a nuclear reaction gives off some thermal energy, मतलब वो एक exothermic reaction बन जाता है, exothermic तो नहीं पता नहीं क्या ना चाहिए, लेकिन it gives off some heat energy. Nuclear fission reaction में होता है, the heat energy then boils the water, steam produce होती है, and that then rotates the turbine. In essence, every single time there is going to be a turbine that rotates and then it results in the cutting of magnetic field. Wind turbine में भी ये होता है कि the turbine is moving, the coil then starts cutting those magnetic field lines, electricity is produced. Tidal barrages में again same thing. एक dams के साथ भी ये होता है कि water is passing through, it rotates the fan blades in a certain direction, the coil moves along with it in the presence of an external magnetic field, and again some electromotive force is produced. Okay? So it's the same concept that बार-बार apply होता है. Inshallah next time we'll be discussing AC generators. ठीक है?